For most of our lives, we've kind of taken one thing for granted. The computer you buy next year is going to be way, way faster than the one you have today. But what if that golden rule just broke? Well, guess what? For the most part, it has. And the story of why is way more fascinating than you might think.
I mean, for half a century, computing performance was on this unbelievable exponential ride. And then, all of a sudden, it wasn't. The party just stopped. So, what happened? Why did the relentless march of speed suddenly hit a brick wall?
All right, so to understand the end, we have to go all the way back to the beginning, to this miraculous era of growth we call the golden age of scaling. This was a time when it honestly felt like engineers had some kind of magic wand. Every single step on this path was a massive, massive leap. I mean, we went from these clunky mechanical relays in the 40s to glowing vacuum tubes, then to tiny, super reliable transistors, and finally the absolute game changer, putting thousands, then millions of those transistors onto a single piece of silicon, the integrated circuit. But see, as chips got more and more complex in the 80s, they started getting seriously hot. They were drawing power constantly, even when they weren't doing anything. The solution was this brilliant new circuit design called CMOS. And its big secret? It only used any real power when it was actively switching from a 0 to a 1. This one trick solved the power problem and just opened the floodgates for making chips unbelievably complex. And this was the magic formula that powered the industry for 3 decades. It's a principle called Dennard scaling. Think of it like this. Every time engineers found a way to shrink the transistors, they didn't just get smaller. They also got faster and used way, way less power to do their job. It was the ultimate free lunch. You got more performance, and the power consumption per area stayed the same. It seemed too good to be true. And for a long, long time, it actually was. But you know how it goes. No free lunch lasts forever. Eventually, all that engineering brilliance slammed headfirst into the unyielding, stubborn laws of physics. And this is where our story takes a really dramatic turn.
You see, the market was screaming for more and more speed, so designers got aggressive. They started cranking up the clock frequency. Think of it like the heartbeat of the processor, way beyond what Dennard scaling's free lunch model really accounted for. They were basically borrowing performance from the future, and physics was about to send them the bill.
Now, to really get what went wrong, we need to meet the villain of our story: power. In computing, it's simple. Every single watt of electrical power you pump into a chip has to come out as heat. Power isn't just some number on a spec sheet. It is a thermal problem you have to solve, or things literally start to melt. And here it is. This chart right here is the smoking gun. Just look at that insane climb in clock speed through the 90s. And then, boom, a complete flatline. Around 2005, the frequency just stops going up. This is the power wall made visible. We simply couldn't cool the chips anymore if we tried to make them any faster. So what was the technical culprit? In a word, leakage. The transistors got so microscopically tiny that they just couldn't fully turn off anymore. They started leaking a little bit of current all the time, kind of like a faucet that you can't stop from dripping. Now imagine billions of those tiny drips all at once. It adds up to a flood of wasted energy and just unbearable heat. And this wasn't just some temporary blip. In 2011, the National Research Council basically made it official. They said the era of exponential speed increases for a single processor was over. Done. Game over. Or was it? The industry, facing this massive crisis, made a truly brilliant pivot. They realized that if they couldn't make one engine more powerful, maybe they could just use more engines. I mean, this was the billion-dollar question, right? The demand for more performance certainly hadn't gone away. So if raw speed was off the table, where was all this new power going to come from? And the answer was to completely change the philosophy of chip design. Instead of building one giant, hot-rodded V8 engine of a core, they started putting multiple, smaller, more efficient cores on a single chip. From now on, performance wouldn't come from raw speed, but from parallelism, from doing lots of things all at once. This multi-core revolution totally saved the day. It's why performance continued to climb. But, and this is a huge but, it came with a massive catch. All that new performance was only there if your software was smart enough to actually split its work across all those new cores. And that turned out to be a huge new challenge for programmers.
But even multi-core wasn't the final answer. For some of the world's most demanding jobs, even a general-purpose multi-core chip was like using a Swiss Army knife to perform brain surgery. A new revolution was needed, one that was all about radical, absolute efficiency. So this brings up a totally new way of thinking. Your general-purpose CPU, right? It's designed to do everything pretty well. But what if you only need to do one thing over and over and over again as efficiently as humanly possible? Well, enter the ASIC. That stands for Application-Specific Integrated Circuit. This is a chip that has been stripped of everything it doesn't need. It is custom-built from the ground up to do a single task with just mind-blowing efficiency. It's not a Swiss Army knife, it's a perfectly crafted scalpel designed for one job and one job only. And the sheer scale of the difference here it's just staggering. A general-purpose CPU is way down at the bottom of the efficiency ladder. A more specialized processor, like a DSP, is better. But an ASIC? It's not even in the same league. The efficiency gains are just astronomical. And this has a staggering real-world impact. Get this. Researchers figured that building a supercomputer for climate modeling with general-purpose chips would demand 179 megawatts of power. That's enough for a small city. The same machine built with custom ASICs, just 2.5 megawatts. That's not just an improvement, that's a whole different reality. So where does all this leave us? Well, the era of the free lunch from Dennard scaling is long, long gone. The pivot to multi-core definitely bought us some time, but the next great leap in performance seems to be pointing in one very clear direction. Now, don't get me wrong, there is some really exotic research happening to find a successor to our current CMOS technology. We're talking about wild stuff like tunneling transistors and spintronics. But being realistic, these are probably decades away from being practical. For the foreseeable future, we have to work with what we've got. And that brings us to our final thought. For half a century, we've lived with this idea of a universal general-purpose computer. But if the only real path forward is to build thousands of different specialized chips for thousands of different tasks, are we witnessing the end of the computer as we've known it? It's definitely something to think about.